Okay, going to start off with an investment problem here. Ed invests $100 at 5% interest for 8 years. We want to find the final amount if it's compounded annually first off. Okay, so compounded annually, we can use our basic exponential growth formula. Looks something like this. Okay, A is the initial amount, Y is going to be the final amount. I don't know the final amount yet, but I know the initial amount's 100. The rate is going to be 5%, and write that as a decimal, so 0.05, and then the time is 8 years. And then we just simplify this. So 1.05 to the 8th. Remember, don't multiply before you do the exponent. Got to do the exponent first because we got to follow PEMDAS here, right? So doing this part first, and I'm going to use a calculator for that. So let's see, 1.05 to the 8th, and then multiply that by 100. And since we're talking about money, I'm going to go to the nearest cent, so I'm going to call that $147.75. Okay, so as we discussed in previous sections, the more often you compound, the more money you should have. So let's see what happens when we compound quarterly. This means we're going to calculate the interest 4 times per year. That's 4 quarters in a year. Okay, so I've got a souped up version of that exponential growth formula. It has the n's in it, so there's an n underneath the r, and as a denominator, there's also an n in the exponent in front of the t. Okay, so y is my final amount, a is my initial amount, still 100. My rate's still 5%. That's going to now be the numerator of that fraction. And then 4 is the number of compounds per year. And then got a 4 up there as well for 8 years. By the way, you could use this formula up here. It's just there would be 1 compound per year. So the n's would be 1s, and they wouldn't really do anything. That would actually simplify to that formula, right? Okay, so let's start simplifying this. Okay, I'm going to start working on the fraction. So 0.05 divided by 4 plus 1. So the contents of the fraction is 1.0125 once you simplify it. And then 4 times 8 is 32, so that's my exponent. Okay, so I'll take the 1.015 raised to the 32nd and then multiply that by 100. And I was expecting more than $147.75, and I did. I got a little bit more, $148.81. Okay. All right. Now, what we haven't done yet is compound continuously. So that means that when we're compounding continuously, that means that we're constantly going to be calculating the percentage and adding it back into the pot. Okay, so it might seem impossible, but there's a number that you can approach when you compound continuously. There's also a new formula here, so we can't use this one with the n's. We're going to have to use something that looks like this. Okay, so a lot of these elements are similar. Got the starting amount, final amount, that's the rate and the time. The new component here is E, all right? And E is actually just a number, like pi is a number. Pi is 3.14 and goes on, right? E is also a number. It comes out to about 2.178, but it's an irrational number that goes on forever. This is a very famous number, kind of like pi. It comes up in lots of different applications in the real world and in mathematics. And I don't want to talk about it too long because I could spend 40 minutes talking about where it comes from. But let's just, one thing I want to show you is that it should be programmed into any not a really simple calculator, but a graphing calculator or a scientific calculator. So, you know, this calculator, it's got on my calculator, those green letters, and there is an E in there, but that's not what I want. That's just text. What I want is above the division symbol. That might be hard to see, but above the division symbol on this, it's a lowercase e. I almost always write in uppercase, but this is lowercase. The E is always written in lowercase. So I'm going to hit second and then divide, and then that number that little e shows up on my screen. And if you press enter, I get that 2.718 number. So actually, it is rational. I said it's irrational before. It does repeat after the. You can see there's a pattern that's repeating. But anyways, it's about 2.178. Okay. So what we're going to do, our initial amount is going to be 100 still, and I'm just going to write E there, okay? And then the rate is 0.05. The rate is now going in the exponent, and the time is going to be 8 years, okay? So it's tempting to do the multiplication first, but remember this is 100 times E. Before I do that, I want to do the exponent. So I'm going to start with that, and the last thing I'm going to do is multiply by 100. Okay? So I'm going to take E and raise it to, and 0.05 times 8. You can put that in parentheses to make sure it stays in the that whole quantity stays in the exponent. Okay? So Y is going to be about 100 times 1.49. Okay, I'm not going to round as I go. I still got that nice long decimal on my calculator, so I'm going to take that and multiply that by 100. And now I can round to the nearest cent. And I did get a little bit more. Remember, we had 148 and 81 cents. Now we got 149, and it's a little disappointing. You might think that you would be infinitely wealthy if you're compounding continuously, but it's gonna max out with the compounding at $149.18 under those circumstances if we're doing 5% for 8 years. Okay. Yeah, so you just have to know the formula, and you have to know how to use your calculator to find the E. You can use 2.17718. I put 178. Oops, this should have been 2.718. You can use that, and it'll get you close enough usually on money problems. But it's better to use the built-in E function. It's going to get you a more accurate answer. Okay. All right. So now we've got something called a natural log, and a natural log is just a log with a base of E. Okay. That's what a natural log is. Okay. And you could write it like this. Let's say we had log base E of 7, but it's not actually written like that. So this comes up all the time, natural logs, just like common logs do. But usually what we're going to do, instead of writing a log base E, we're going to write in cursive. I guess you don't have to go cursive, but that's how it's usually done. So it's this ln E. So ln is equivalent to log base E. Okay, so you just have to know ln, that's for natural log, that means log base E. Okay, a common log is a log with base 10, right? And we've covered this before, but just to contrast these two. So this would be log base 10 of 7 or whatever, the contents could be whatever. And for these, you don't have to write the base, because that's our most common log. Okay. All right, and both of these, and I put, oh man, I meant log base E is the ln part, and the contents here should have been 7. Sorry, I'm messing up here. All right, log base E of 7 is the same as the natural log of 7. And this is something that I can put into a calculator, okay? And this is important that you know how to do this as well. So the log button is right there, right? And right beneath it, next to the 4, is the ln button. That's what I want. So if I want the natural log of 7, I just hit ln 7. There's a special button for it because it comes up so often in mathematics. So we got a this would be about 1.95. Okay? And while we're at it, let's just get a decimal approximation of the log base 10 of 7. You just hit log 7, and that's about 0.85. Okay? All right. So If you are comfortable with the logs we've already done, there's not really that much that's new with these common logs. It's just you have to know, with the natural logs, you just have to know that a natural log means you have a base of e. But then all of the properties and methods we've been using with the other logs are still going to apply, okay? So on this next problem, okay, I've got log base of e on both sides. And for this to balance out, I need those contents to be equivalent, right? So the only way this is going to work is if both those parts I circled are equal to each other. So you don't have to do much with logs here if you just realize, oh, you have a log with the same base on both sides of the equation. Then I got a pretty simple equation to solve here. Actually, I'll subtract x from both sides. You can't tell in the video, but it's early in the morning for me here, and I think I haven't woken up yet. I'm making lots of little errors here. Okay, so then I get x equals 2. Okay. All right, so let's try another. So remember, this is log base e. And hey, I've got two different logs with the same base. So that means I should be able to combine these two into one log. So this would be natural log. And then when I'm adding logs of the same base, you multiply the content. So x times 3, I could write x times 3, but let's just simplify that to 3x. Okay, so I've combined this into one log. Now I'm kind of stuck. I can't put natural log of 3x because we don't know what x is. But what I can do is convert this. You have to know that this means this. You wouldn't have to write that out, but you'd have to know, looking at this, that means log base e. So now I'm going to convert this into exponential form. So e raised to the 4th, e is my base, right? The exponent is the isolated part, though, there. And then the contents of the log go there. And now I should be able to solve this for x, right? I've almost got x isolated. All I have to do is divide by 3. So this is going to be e to the 4th divided by 3. And that's something I can figure out with my calculator, right? So let's try that out. Okay, so there's the E button above the division symbol. Above the LN button, the natural log button, there's e to the x. So, you know, I could do e and then raise it to the 4th, and nothing wrong with that. But we're going to be raising e to power so often that there's a button just for that to save you a little time. Okay, so I've got e to the 4th. I'm going to type that in. That's what e to the 4th is. And then I'm going to divide that by 3. Don't round as you go, right? Wait till the end of the problem to round. And so I'll call, if I'm going to the nearest hundredths, I'll call this 18.20. Okay. All right, let's try another. So this one's a little different. We're going to find, I'm now finding the inverse of these three different functions. So this is kind of going back to another topic. So you're going to switch the x and y's and then solve for y. So I'm going to try to get the y by itself. So I can subtract 1 from both sides. That's a little closer towards isolating the y. Okay? And now we're kind of stuck with our old school algebra. You can't just take the square root, because then I'd have the square root of 3 to the y. That's not going to help me out. And I can't take I can't use y as an index either, because it's just going to get too complicated over there. So, and I won't be able to isolate the y like that anyway. So what I'm going to do is convert this. Okay? Once you've isolated the y as much as you can, convert it to the other form. So this is an exponential form. Let's rewrite this in log form. My base is 3. Okay? The exponent's going to get isolated. That's what I want to happen. And then x minus 1 is going to become the constants of the log. And make sure you put x minus 1 in parentheses, because I don't want it to just say log of x and then subtract 1 afterwards. I want to show that the negative 1 is part of the contents there. Okay? And this is in exponential form. And I'm just putting it back in function notation. So here is the inverse of this. So when you take an exponential function, its inverse is always going to be a log. Okay? So let's see what happens when we've got an exponential function that involves e. So same method here. I'm going to switch the x and the y. Okay? And I'm going to start isolating the y. Well, I can subtract 1 from both sides. just like in the last problem. Okay, now I can't really do anything with the e and the y, but I can isolate e to the y at least by dividing the whole equation by 2. Okay, now you could split that into two different fractions, x over 2 minus 1 over 2, that's fine, or you could leave it like it is, it doesn't really matter. Okay, and now the only thing I can do is convert this into log form. So let's see. My base is going to be e. Okay, the y is going to get isolated because that's the exponent, and then the fraction is going to be the contents. And again, use parentheses to make it clear so it doesn't look like e to the second is the base or something like that. Okay, so, hey, wait a second. I've got log base e. Well, that's my natural log, right? So I wouldn't want to leave it as log base e in an answer. It's going to equal this, okay? So the moral of the story here is that when you've got e raised to the x, and you take the in your equation, you take the inverse, you're going to end up with a natural log. Just put it back in function notation there. Okay. So hey, here we've got a natural log. So if these two were inverses, I'm expecting to get e to the x or something involving an e when I take the inverse of this. Let's see if that happens. Let's switch the x and the y. Okay, I'm going to start isolating y as much as I can. I can just subtract 3 because that 3 is a free agent. It's not trapped inside the log, right? So I can rewrite this as x minus 3 equals the natural log of y. And then I want to convert this. So you got to remember this means log base e of y. So now when I convert this, e is going to be my base. Okay, my exponent is the isolated part, so my exponent is this whole quantity. So e to the x minus 3 equals y. Okay, and now I've got y isolated, right? That's what I wanted to happen. And here we go then. Okay. That's all I have for today. See you next time.